Up next, we have Aditya Tripathi and Judy Wang from VMware. They'll be talking about running and handling persistent data in a multi-cloud environment. All right, I'll let them kick it off now.
Hi, everyone. It's good to see you. My name is Judy. I am a product manager at VMware, and I am working on the VMware Tanzu SQL project.
Hi, everyone. My name is Aditya Tripathi. I'm also a product manager at VMware, and I work for our Tanzu data services teams.
Great. Today, we'll be talking about how to run persistent data in a multi-cloud architecture and certain considerations that you can make for your data modernization strategy. So to kick us off, I will start by going through our agenda. So to level set, we can first define what multi-cloud even means. I think oftentimes it's conflated with different other terms like multi-site, multi-region. So just to clarify what we mean when we say multi-cloud. And then we'll go and do a diagnosis of where we think multi-cloud is today at the enterprise layer. And then Aditya will take you through a framework for how we think is the right way to approach running data on multi-cloud. And then finally, I'll take it home with a couple examples just so that you can solidify this framework and see how it can be applied. So what is multi-cloud? To us, a multi-cloud architecture simply means that applications and workloads are distributed across multiple cloud computing environments. And so this is a hybrid of on-prem footprint as well as public cloud footprint. And so when we say enterprises are moving to multi-cloud, usually the easier approach is to move stateless applications first. As you can see in this example, a company who's moved some of their workloads to GCP, and they've also moved some to GKE as well. But actually, a more accurate representation of what's going on here looks like this. So while their stateless applications have become cloud native and microserviced, many of them, if not all of them, still need to connect to a giant enterprise RDBMS like iSeries DB2 or Oracle. And this can have a whole slew of problems and complexities. And is the reason why many companies need to start thinking about modernizing their data architecture into something like multi-cloud. And so in order to start thinking about multi-cloud, what we actually need to do is to break down those data workloads into smaller, more manageable and purpose-built services. But if we don't take an organized approach, then this problem can become quite intractable. Should we do active-active or active-passive? Which component should do the data replication? Is it the application layer, the message queue, the database? What happens when there's high network latency? Is my architecture able to be resilient to that? And so I'll let Aditya take over and talk about an approach that we can take to think through these problems.
Thanks, Judy. So the way we thought about this conversation is that we wanted to present to you a high-level framework for how you could break this down on your side and come up with an approach that works for you. We've taken a theory of constraints approach. So essentially that is identifying what constraints act within your problem space, figuring out where those constraints, what the problem space is bounded by, and then taking a three-step framework to solve for the problems. So we'll first identify business outcomes. What does the business actually want to achieve? Then we'll identify certain limiting factors. These could be business factors or these could be technical factors. We'll prioritize certain trade-offs in terms of what behaviors users expect from applications, and then certain day-to maintenance trade-offs, etc. And then we brainstorm a few solutions. We'll end this conversation with Judy actually stepping through a couple of examples that apply this framework. So to start with, in terms of business factors, from our experience in talking to customers and users, I think the first thing that needs to be clarified is this conversation about DR and high availability. So disaster recovery versus high availability. Disaster recovery, as we're aware, is how quickly can a system come back up from a failure. So when a hurricane hits or an earthquake comes around, how quickly are your systems back up within the RTO, the recovery time objective? And how high availability is about the high nines or about the nines. Are you always available and serving customers? So that's always a conversation between the sort of trade-off that customers want within these two bounds. Uh, the next factor that tends to come up quite a lot is the geoquery response time. Where are customers and where is the data stored? What sort of latency do we need? Do we need 2 milliseconds or do we need 200 milliseconds? That sort of behavior, sometimes a quick response time can be very expensive to achieve. You need expensive hardware, applications would need to be tuned, databases would need to be structured. So there's all of that. And then there's considerations around the bursty traffic pattern. So every application tends to follow a regular sort of normal traffic pattern. But then consider, for example, with e-commerce, people tend to get paid around the end of the month. And once payday actually happens, e-commerce applications will typically see a burst in the traffic or higher traffic spikes in the first week of the month when people tend to make purchases. So figuring out the cyclicality of your application and figuring out when your bursty traffic tends to happen is also useful. And then lastly, rounding up this list of business outcomes is data sovereignty, which increasingly is, do governments care and do governments govern where the data for their citizens or their concerns lie? And whether you'd like to solve for data sovereignty using manual or programmatic methods. This is by no means a full list, but this is an important list of conversation starters. After business outcomes, we want to talk about limiting factors, which could be business or technology limiting factors. Within business factors, increasingly in a COVID world, you might have to worry about what does the free cash flow for your business look like? Does the business have the ability to spend more capital expenditure or operational expenditure on cloud purchases? Uh, there could be influence factors. So, for instance, are certain teams within the business more influential than others? Like, for instance, in banking examples, certain teams might want to lead from the architecture out. Do you have the skill? Do you have the expertise or the skills to make the transition happen, or is there a skills gap? And then there are technical limiting factors. Like, for instance, what is the sort of geography that defines where your data sits, or the configuration that you want from your machines that are in multi-site configurations? Uh, Looking at limiting factors, a couple of other things that are worth a mention. The heterogeneity of your stack. Like, for instance, how many disparate components are there within the stack? Like, for instance, certain applications need a connectivity to transactional databases. Other applications need the ability to work against a document store. And then legacy bits and pieces or slices within your stack. For instance, are there older applications that you need to worry about? Is all of the data eventually persisted into a mainframe? So these things tend to come up, and these could be limiting factors that you might need to worry about. After we've seen business outcomes and we've seen certain limiting factors, we would like to look at trade-offs. So, for instance, there is the sort of classic CAP theorem driven consistency or availability debate. So, for instance, do you want quick recovery for your applications, or do you want for your applications to be always available? And this usually is a conversation with all of the teams that deliver user-facing components. So, looking at your use cases, you'll be able to figure this out. Uh, then you look at maintenance and management trade-offs. Like, for instance, with a very complex solution, you might have to worry about spending a lot of management bandwidth to manage those kind of systems. If you're already spending a lot of time and effort on capacity planning, then going to the public cloud will actually solve that for you. And then how are you managing failovers at the moment? Are you running active passive failovers, which are potentially being executed by hand, or can you move to active active, which could be automatically done? The other thing that you want to look at in terms of trade-offs is the kind of services marketplace experience that your public cloud provider offers. So these days, all of the public cloud providers tend to have a variety of plethora of services. There are various types of systems available for batch ingestion, stream ingestion, real-time data processing, data lakes, data analytics. There's a whole wide range out there. So you might want to actually quite intentionally look at your public cloud provider to see if their marketplace suits, if one of their marketplaces tends to suit your use cases better. And then the last thing is around ownership. What sorts of switching costs and what sorts of data ownership constraints do you want to work against? Like, for instance, are you happy to hand over your data to one of the public cloud providers? Or are you likely to keep that option with you, retain that option to be able to move your data around within different public clouds? And with all of those points, so the business outcomes, the limiting factors, and the trade-offs, you can come to the stage where you start to brainstorm solutions. You can look at data replication options. So you can look at active-active versus active-passive, or whether your use cases demand a synchronous or an asynchronous application data exchange format. Increasingly, we've seen customers look at near-far as a replication option. So for instance, having two data centers in close proximity and having an active-active replication between two nodes that are quite near each other, which is not as expensive, and then having an active-passive replication with a node which is a little bit far away. So that tends to provide you with the best of a little bit of the both worlds. You also want to look at your cloud footprint. So for instance, are you looking at a full on-prem footprint, or are you looking at a hybrid public-private footprint, or a full public cloud footprint? And the last consideration in this entire list should be specific technologies. So for instance, are you able to use certain caching technologies for replication and buffering use cases? VMware Tanzu's Gemfire application is actually quite a good one for those kinds of use cases. Looking at messaging queues, this provides you the ability to use a messaging queue as a bus between architecture, so that bridges the gap between all of the heterogeneous components within your stack. And then maybe event logs that allow you for the ability to capture event logs and for figuring out sequence of records. Uh, at the end of this list, you could also potentially look at purpose-built technologies. So for instance, things like Amazon Aurora or Google Spanner that are actually designed from the ground up to be highly distributed data solutions. Now that we've seen business outcomes, we've seen certain limiting factors, and we've seen some of the trade-offs. Let's look at a couple of examples that Judy has planned for us using the same framework.
Thanks, Aditya. So it might be helpful to walk through a couple examples just to solidify our understanding of how this approach would work. So the first example that I have is just traditional disaster recovery. So in this example scenario, we have a business with currently just a single environment in one data center, and all traffic is handled by that one environment. But as you all may be familiar with, there are certain business critical applications that have really tight service level agreements, SLAs. And these types of applications must have a recovery strategy at a data center wide level. So let's say, for the sake of this example, that they have a recovery time objective of 20 minutes and a recovery point objective of 4 hours, which is what we've seen to be pretty common across customers that we've talked to. In this case, they also have to deal with two main limitations. Of course, there are others, but these are probably the largest blockers. So the first one is the inexperience of their team, both their platform team as well as their data team and dev teams. While they do have some experience using, let's say, SQL databases, they don't really have the expertise and haven't really gone through the training of using something complex, such as Kafka, for example, or even Gemfire. So they want to minimize operational responsibility to the teams. And then secondly, hardware limitations. They currently only have one private data center. And just given the time constraints and the budget that they have, it might not make the most sense to acquire hardware and install a second data center for the sake of this single application. And then finally, around trade-offs, this business prioritized what was most important to them, and then finally what's important but the least important. So first off, above everything else is data consistency. This business would rather we experience downtime rather than present inconsistent data. And then secondly, the minimizing management due to the inexperience of the team. And so the overhead of operations should be kept to a minimum. Thirdly, around availability, like I mentioned before on the RTO, 20 minutes of downtime is okay. And it's definitely not as important as consistency in this example. And then finally, around query performance, since this isn't an application that, let's say, doesn't directly interface with the client, and the client doesn't expect fast responses, it's not necessary to have sub-second query response times. And it's a trade-off that this business is willing to make. So how do we want to go about attacking this problem. In this case, the solution is fairly simple, I believe. So this is their existing on-prem data center. And instead of provisioning another on-premise data center and taking the time to do that, let's put the workload on the public cloud, because it's just a credit card swipe away, and you can get that set up fairly quickly. In this case, let's install Tanzu Application Service on both of these environments so that we can do away with some of the operating costs and complexities that the team was concerned about. And then finally, in order to replicate data from your primary site, which is on-premise, to your secondary site on the public cloud, we can install Tanzu MySQL, which is a service that adds a little bit more automation and value to just an open source distribution of MySQL, again, to minimize the operational costs and complexities of running a database that your team might not be familiar with. And just as a thought exercise, if this company needed to follow specific data sovereignty regulations, such as GDPR or other regulations that require them to keep their data localized or domestic, then they might not be able to spin up a public cloud environment because GCP or AWS might not have data centers in the correct regions. And so this is a trade-off, an example of a trade-off that needs to be made. If you need to follow legal compliance laws, then you might not be able to optimize for convenience or automation. So that was a simpler example. I'd like to take us through another example, which is a little bit more complex and maybe a little bit more realistic to what you might be dealing with, which is point of sale. And this is extremely common across many retail businesses who want to modernize. So in this example, the primary business outcome is that the applications need to be geographically co-located at the point of sale location. And the limitations that we're working with here are mostly hardware and network. So these point of sale locations need to run or have historically run on bare metal environments. And so they need to have lighter environments that these locations can handle. And then secondly, there's always the risk of disconnect in network. So these point of sale locations might periodically lose network connectivity to the central environment or to the web. So how can the business continue running in those scenarios? And then the final limitation is around the inertia of legacy data platforms. All of their transactions must eventually be stored in a system of record that acts as the single source of truth. So how can we maintain that and tackle the problem of distributing your source of truth at a later time? So the trade-offs that were prioritized here is pretty different from example one. The first and utmost importance trade-off or priority, I mean, is availability. The system must not be available because since this is a customer-facing application, there are customers waiting at the cash register for a response from the system. And similarly around query performance, whereas before sub-second queries weren't very important in example one, in example two, for the same reason, with customers waiting at the cash register, you can't have queries taking 30 seconds after you swipe your credit card. And then finally, around data consistency, this is actually something that can be traded off because while it is fairly important for each point of sale location to have rather consistent data, let's say on pricing or on certain discounts that are applied, it's not necessary for every single transaction to propagate to every single point of sale location, as long as it eventually makes it to the centralized system and is updated, let's say nightly, then that's fine. So what approach can we take here? The architecture here is a little bit more complex, but I'll walk you through it. The central environment has better hardware and has more heavyweight operations that need to take place. So for the sake of this example, let's say it does pricing, promotions, and taxes. And each has their own database to store this data. So to tackle the legacy data platform problem or limitation, we have the system of record that's lying somewhere else. And we can deploy a microservice that pulls data from each of these databases and feeds it and ETLs it into the system of record. For the edge environments, since they are running bare metal and need to be more lightweight, instead of running something heavy like Tanzu Application Service, instead they can run Kubernetes. A containerized platform is definitely much lighter and cheaper. than running VMs. And each of these applications can handle transactions at the cache register. And so in order to tackle the network connectivity problem, we can deploy a cache such as Redis for each of these applications. And these caches are loaded with data using a nightly cron job, such that these caches can store that data from anywhere between 24 to 48 hours, such that if there is any network connectivity problems between an edge environment and central, then these environments can continue to work using the data stored in the cache. And when connectivity is restored, then they can sync back up with the central locations. On the topic of high availability, just as another thought exercise, if a single Kubernetes environment is not enough for HA and needs a higher level of resilience, then you can always deploy multiple instances of your Kubernetes cluster, such that if one of the clusters goes down, you can reroute to the second cluster. And it's fairly cheap since it is a containerized platform. Some other considerations that we could possibly make. Let's say you want to replace your nightly cron job with something like Kafka. And the reason why you might want to do this is if you actually do want live updates to each of your edge environments. Let's say a flash sale lasts 30 minutes, then you can have Kafka help you propagate those changes live to each of the edge environments, which would be a lot more complex to do in a cron job. But the trade-off that you have to make here is that it's much easier to wrap your head around a cron job than it is to understand the inner workings of Kafka and be able to manage it. So does your team have the right expertise to have this added complexity? Another alternative solution, depending on what your priorities are to move the Redis instances from on-prem to the public cloud as well. And the reason why you might want to do this is if you don't want to manage upgrades, security patching of your Redis instances. And if that's the case, then you might want to move it to the public cloud since AWS, GCP, and Azure and other clouds offer Redis as a service in their marketplace. But the trade-off that you make here is that you are relinquishing control of your data to the public cloud. And also around network connectivity, since the caches are no longer co-located with the applications in the edge environments, if the edge environments somehow lose connection to the public clouds, then you would also have to suffer downtime. So these are the trade-offs that you will ultimately have to make. And the different permutations are virtually endless. So I guess the main takeaway here is that neither Aditya nor I are experts, and these are not the end-all be-all answers. These examples are actually quite simplified. So please do consult an expert if you are thinking about moving your data onto a multi-cloud architecture. That's the reason why we have VMware Pivotal Labs, is that they can help you think through these really complex problems. But if you take the time to go through this framework that Aditya walked you through, then thinking through these problems is a lot more manageable. That's all that we have for you today. Thank you for listening to our talk. And please don't be a stranger. You can contact us at our emails here. Thank you.
Thank you.
Thanks, Judy and Aditya. Yeah, and also don't forget, everyone, you can head over to the Q&A and ask them questions right now if you want to. And there's also a Slack channel as well for the session.